Well, welcome back. This is the Flat Earth Genius. We're back for part two of this very first lesson in the Flat Earth that I'm presenting to you tonight. I went through my introduction, explained who I am, a little bit about my background and where I stand in the whole religious thing, and I went through some things we need to do as a community to kind of pull together and coordinate and work together. We really need to administrate some of these things, and let's find out who among us, just like in anybody, like in the church. I come from that angle in a way, um, not from a religious perspective. Yeah, I came out of the religion, but I still see things in a perspective of a church, the true church. When I say church, I mean the true church. And we have many gifts, and each one of us possesses a particular gift, and those things kind of work themselves out. I think what we see in this whole drama amongst us is us not recognizing the gifts in each other and and lifting up that person's gift, but instead feeling a little bit uh, intimidated by what other people are doing because maybe they're getting notoriety, or there's just the whole human side of this is really kind of taken away from what this is about. This is about this flat earth we live on, and not this ball here. We don't live on a ball, we live on a flat earth. It's not about YouTube hits. It's not about anything at the end of the day. Yeah, those things are great, man. I want to have a me. I want to be the biggest dude on YouTube for the flat earth. Why wouldn't I be, right? But I can't let that take away from this flat earth we live on and not a ball, because this is what it's about. This is what we're here for. We're not here to make money. We're here to present that we've been lied to for hundreds of years. We're living in the biggest deception possible. And like Flat Earth Asshole says, I love it, they're taking our money. If for no other reason, they're stealing us. They're robbing us blind. So let's get our differences aside. This drama, bullshit. Let's just bury that stuff, man. If you don't like somebody else, that's fine. You don't have to like them. Just respect them and honor them anyways as a human being, as a brother on this planet. I'm sorry, I said planet. See, the religion of living on this is real deep, and it takes a while to work itself out. You'll hear people say planet all the time on these videos, and it happens. It feels like I just felt like shit just then because I said that. But it happens, deal with it. But so, and I went through some bogus theories in part one. I'm just recapping. I went through some bogus theories talking about from the book Terra Firma, where it talked about the train track would have to be going up a 3-mile mountain, which is just simply not true on this model. You have to use this model and what they present in its physics, because you can't say it wouldn't work on this using their physics. You have to use their physics if you're going to use their model. And the whole train track thing is just garbage. It's a garbage proof. We don't need it. It's not true. If this was the model, the train track is never going over a 3-mile mountain. If the train track was built level, then the train is level, even around the curve, because this is flat and level. This is not elevation changes here. Even on a ball, this is flat and level, because it's in relation to the center of that ball, where gravity comes from. We have to use their model. They have this magic, wonderful force called gravity, pulling everything in. The very center of that ball is this spinning mass of some shit. They don't know what it is, but it pulls everything to the center. It's like everywhere, all the way out to the fucking space, pulling in the moon and shit, But the point is that train is flat and level anywhere on this, as long as it's at the same elevation. You can be up here, as long as it's in the same elevation, it's flat and level. So we went over some bogus science, and now I would like to, yes, okay, this is where we're at now. Now we're up to speed. I'm getting excited, man. This stuff excites me, bro. You're sitting here in my living room with me. This is what I do. Like, I wish you were here for real. Man, a flat Earth asshole was sitting here, and Jaron Island, Jaron, that's your name, or Eric, or Math Powerland. I'd love for all of us to be here and just learning, for just balancing the ideas, man, in harmony. That's how we're gonna work through this. We gotta pull our minds together and stop the drama. So here's some of my ideas and theories. I'm not saying I'm taking credit for any of these. Some of them I've not heard elsewhere, and they could have been presented 1,000 times before. I'm just saying I haven't heard. Like I said, I'm new. So if they've been presented, then link it in the video and say, hey man, somebody already did a video, and I'll look at it and see if it answers it or presents it. If it does it better than I could, then that's what I don't need to repeat stuff somebody else has done better than me. So, but here's some things that I wanted just to present my thoughts on, and maybe I see things from a little bit different perspective. Like, everybody has their own path in life. I've went through my journey. I've had my own education. When I was a kid, just a little bit about that. I grew up in Central Florida, the big city in Central Florida, the biggest city in Central Florida, and when I lived back in the days of yard sales, back in the early '80s, late '70s, we would all Saturday morning, it would be yard sale day. We'd get up early Saturday morning, and me and my dad and brother would go in yard sale. And my dad would give us, or we would have earned from working throughout the week in allowance, we'd have some money. And almost always, I would come home from yard sale with a stack of books or a stack of records, vinyl records. Classical, if I could find them. I loved classical music, but then I would get jazz like Herb Alpert and Neil Diamond and Gordon Lightfoot and anything I could find. I listened to all types of music, everything from classical to opera to big band, and I loved it. But I would buy books, and what I would buy is educational books. Like, I would buy college textbooks. I love college textbooks, especially ones on physics and engineering and geometry and trigonometry and all the math sciences. I would study. My mom had Encyclopedia Britannica, the big set. We had the however many volumes there was. There was a bunch of them, 20 or 30 books. Beautiful illustrated, colored illustrated. I ate the encyclopedias up. I can't tell you how much time I spent studying this thing right here in outer space and being mesmerized by the whole thing. But that was my childhood. I love physics. Physics is my thing, and now, I'm not saying I know all the terminology and stuff, because I didn't pursue it. I went through electronics engineering in college, but I only went through a year of it, and then I dropped out, because I got married early and I had children, and, I had to do what I had to do to make ends meet, and I dropped out. But, that's where I was headed. And and I've worked in construction, most of my adult life, and I grew up in construction because that's what my dad did. So I've got a very, very firm handle on physics and geometry and the mathematical sciences, for the most part. I'm always learning, but I'm just saying I can handle my own. And so I say all that to say I can bring information from a different perspective. So I'm just trying to give you what I have to offer. So I'm going to go through some of my ideas and theories right now. Maybe our little friend over here can give us a hand on some of these too. So it's raining outside. I don't know if you can hear it. What I want to talk about first is the good old-fashioned why do boats in the sun disappear over the horizon? Mainly, more so, why they disappear just like they would had they went around the ball. From the bottom to the top. Now, I know plenty of videos have been done on perspective, don't get me wrong, and this question has been answered numerous times properly. But I'd like to just add a little bit more to that. Maybe I can help give someone a little bit of information that'll make it easier to explain the next time. I'm going to just keep my phone out and use this. But here's what I want to talk about is our perspective. Now, we've all seen the perspective charts in the flat earth videos. You know, you've got your horizon line, and then you've got these lines all coming in. You got your overhead lines and your ground lines, and they meet up here at the horizon, right at eye level. And anything out here comes and meets in at these points, right? And that's perspective. So we look down a long hallway, the walls come in, the floor and the ceiling rise and lower to meet each other into a center point. Eventually, you know, that hallway will just turn into a little dot in the center of our field of vision. And we could agree that that's true. We've all experienced that in numerous ways. But that's not really a good explanation of perspective. Yes, in a hallway or a corridor with walls and ceilings, that's what we perceive. But when we go out to the coast, we're not in a corridor with walls and ceilings. There's only one hard barrier, which is the floor. Your left and your right and your overhead is open space. So everything changes in perspective versus looking down a long corridor. They're just two different scenarios. Yes, perspective is still the same technically, but you're seeing perspective from a different perspective outside versus in a corridor. The hallway, this left and right wall, is your limiting factor. So as that hallway gets longer, it goes down, the walls come into that center point. Yes, because you have a hard point here. And you have a floor that rises up to that hard point, and then a ceiling that comes down to that hard point. So they all meet in that little center dot right there. But outside, you have a horizon with hard ground or water, which is a solid substance, you know, that comes up to it. But you just have ether to your left and to your right and above. So all the way across, you just have this ground. Pretend like you're in that hallway, but just remove the walls. Now you just have a floor and a ceiling. So now instead of your field of vision being like this, your field of vision is like this, with the ground and the sky, except sky is see-through as well, you know, other than clouds. Yes, you'll see clouds, but let's just say it's a clear day. This is the only perspective you have. Now, the only limiting thing is your ground. So now your line of perspective is here. When you're standing here looking straight, keeping your eyes ahead, I can see my finger literally 90 degrees. I can see it sticking straight out from my ear. I can still see my finger right here. And over here, I can still see it because it's on the screen. I got you. No, just did. Let's see. I can see it right here. I moved my eyes. Let me wait to adjust. Okay, there and there. That's literally almost straight out. I can see perspective. My field of vision is that way. I've got a good field of vision. I can look ahead and see. Some people have got tunnel vision, like I got a real wide view. Maybe you do too. But everybody has their own, amount that they can see to the side. Well, so when I'm looking out at the ocean, I'm seeing the horizon way, way out. I'm seeing a long way across. I'm not just seeing a dot like we see everything come together in this chart. I'm not seeing a dot. I'm seeing my horizon is this long line. So now the lines, our perspective lines, don't come to a dot because we don't have the limiting factor of walls to narrow us down. The only limiting factor we have is the water, the ground. So we don't come to a dot anymore. Our perspective doesn't come to a dot. So in other words, I'm using this, but we're on a flat earth. I'm just showing you. This phone, the farther away it gets, if this is a ship, we're looking at a ship, right? They're wide. This ship, as it goes out to sea and disappears, doesn't, disappear into a teeny tiny dot, because there's no limiting factors to make it do that. So we see the full width of it as it disappears. You understand? Yes, it will get narrower, and if it was to go far enough and the ship was not wide enough, yes, it would go down to a dot. Because the ship is its own limiting factor and perspective-wise, too. The farther it gets away, the smaller it gets, right? Just like here. It takes up the whole screen, but as I go away, it's getting smaller and smaller. Eventually, I'll get this phone far enough away where it will disappear from your field of vision. But everything else is still here. That didn't disappear. So what happens is when this ship comes and does this, we don't lose its width because there's no limiting factor to bring that down other than the width of the ship, right? So that's why we can zoom in on our Nikons, which I don't have, but I'd love to get here one of these days, and see the ship, a big old wide ship, and it's still big old wide. It hasn't turned into a dot. It's still wide because our perspective is opened up. But it does do this, right? Why? Why does it disappear from the bottom up? Well, I know we have perspective, and I know, like Rob Skiba did the little magnification thing and pulled the sun away, and it looked like it set just like it really does. And I believe that is accurate. That's a great experiment. That is 100, you know what I'm saying? That's true. But here's another thing on top of that. Like I said, our only limiting perspective when we're out looking at the surface of the ocean is the ground. That's the only hard line there. Everything else is open air. So this ship is in open air. See, these three sides is open. There's only one hard side to this. It comes up and creates a hard line, a horizon, that it's it. When that horizon comes up, when it gets to that eye level point, you're not seeing past it because it's coming up. Everything else that's behind it is behind that line. That's a hard line. Even though that line is as flat as a pancake from here to however far the earth goes, our perspective does this number to the ground and to the sky. It creates a horizon, which is at eye level. Anywhere you're at, it's at eye level. That should tell you we're on a flat plane to begin with. That's a proof of being on a flat plane, not on a globe. That's for a different story. The reason why this disappears by the bottom first is because the point at the horizon is always going to disappear first. Because this part of the ship is still in your line of perspective. It's still in eyesight. But this point down here is at that hard line. And it's at that hard line, which beyond it can never be seen again because it's it's at your vanishing point. This is the vanishing point right here. So anything beyond that vanishes. Well, the ship has to keep going before the top part gets to the vanishing point. You see what I'm saying? The bottom part has already been at the vanishing point. Of course, we're not going around the ball. For real, we're going across a flat, level plane. But if you have all this atmosphere and everything in here, and just by the sheer distance, this is going to get smaller and smaller. But once it gets past that vanishing point, I can keep going straight out. It's going to look like it drops behind. It's because the vanishing point is the key. We have a wide field of vision, not a pinpoint vision when we're looking at the ocean. Down a narrow hallway, yes, it comes to a point. But outside, it doesn't. We have to include all of that. The lines don't come to a point outside. They come prospectively wider and wider apart. If an airplane's over there and flies, it's not going to come to a point here in the middle all the time. It's going to go to its perspective. Now, if we can see it far enough, eventually it will get to a point way, 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 way down the road. But our eyes can only see so far. We're working in a limited field of view. We can literally only see so far, and then it's just the end of it. I mean, there's atmospheric interference, or just our eyes are only so good, and we can only see so far. Some days are better than others, and everybody's eyesight's different. But, you know, everything being equal, not only do we have a vanishing point just because of perspective, but we also have a vanishing point just because of the physical mechanics of our eyeballs can only see so far. And so many miles out, the plane's going to vanish, not into the center, but just because it got too far away and we just lost it through clouds, through atmosphere, or if it's a boat way out over here on the sea, you pull it up, it's not going to pull up in the center of your screen to a little point. It's going to be way over there, just going off into the distance. Your perspective in the sea goes out continuously. It's not just a little point in the middle. So, and what we see is the bottom disappearing first, not because it's going around the ball like this, but because as the farthest it gets away, once it hits that vanishing point, it continues to go straight, but it appears as if it's lowering simply because of the dynamics of our eyesight, because this is going up and this is coming down. So beyond that, this comes down and this goes up, kind of an inversion. So what gets past that almost is kind of like it's going down. It's how optics works, bro. I mean, it's just the way it is. I mean, I didn't invent optics or the physics of it. This is what we can see and test and verify. And so it's a simple explanation that the bottom of a boat disappears first simply because it's beyond the vanishing point, and eventually the next part becomes the vanishing point. And now this is at the vanishing point, and then this, only because it's getting smaller, not narrower. Because the question is why doesn't the sun just disappear into a little tiny dot, right? We want the sun to go, it's a flat earth, look at the sun, it just disappears into a little pinpoint. It doesn't do that, my friends, because perspective-wise, even though it's above the earth, once it gets so far away, it has its own vanishing point. Even a thing in the sky eventually has a vanishing point to our perspective. Well, when it gets to that vanishing point, it's still a big sun. It's still a wide ship, just like the ship got to the vanishing point. It didn't appear, this way to squeeze down to a dot. It slows down this way. It disappears this way, not this way. The sun is going to disappear this way, not this way. The sun is going to do the same thing. Yes, it's farther out, but of course it's huge compared to a ship. If you put the sun next to a ship, even the sun, if it's only 30, 40 miles in diameter, that's huge compared to a ship. But a ship may be 50 miles out at sea, but the sun's a couple hundred miles or a couple thousand, who knows? There's theories anywhere from 300 to 3,000. I'm leaning on the 300 side. I lean on a very close sun, but that's just where I stand. I'm not going to say that's a fact. I don't know, but that's what we need to investigate. We need to do more research, focus on these things. So the sun is setting by the vanishing point just like a ship does, from the bottom up, not from side to side. That's why we don't see it disappear into a little dot this way as it goes down. We want to see it turn into this nice little dot that kind of grows. Oh, it's a dot. It's just getting bigger and bigger and bigger, you know. It's not how it's going to do, because the vanishing point comes way before it ever gets too small not to see. It goes behind the vanishing point when it still has girth. You understand what I'm saying? That's why it does that. I hope that has helped out, maybe give a little bit of perspective. I know somebody out there like Jared or Flat Earth Asshole or Eric or Matt Powerwood or somebody can take that information and present it better. Like I said, this is just a living room conversation. I have a little outline. I'm not scripted here. I don't have videos to upload. Somebody else can do that. It's not really my calling right now. I just want to get this information out and bounce it off of you guys. Somebody else take this information and say, yeah, I see what the Flat Earth Genius is saying here. This is a good perspective. Yeah, you see what I did there, perspective? But I can add this now to my information to further the proofs, you know, because we have to answer to why the ship does this and the sun does this, you know, and I feel like we haven't quite answered that accurately or adequately. We've answered it accurately, but not adequately. And I think by talking about how the vanishing point, and we can do it through experimentations over flat tables and stuff like Rob Steve has done and others, you know, let's do more of that, or do the same experiments that we've done, but explain at the same time how, you know, the vanishing point is this way, but for a large object like the sun, it's going to take a while to vanish this way. But it's not going to, because there's no hard limits on the side. It's only itself is its own limiting by its own size. Just like a ship, it's only limited by its own size. But something in that corridor is limited by the walls, right? So it can only go so far before it goes off into a dot. But there's no limiting agent here, so it can go as far as it wants. Its own limiting agent is its own. Oh, okay. Is its own width. And the sun is real wide and big, so it can go a long way before it ever disappears width-wise. But it's going to disappear because our vanishing point is at a fixed distance from us. It's not. It doesn't change because it's the sun. The vanishing point's a lot farther. No, when it gets to that level, that's our vanishing point. And from that point, every little bit it goes, it's going to appear to vanish. Even though it's going on a trajectory, it's going straight like this. From our perspective, it's going like this. It looks like it's dropping, even though in reality it's doing this. You've seen the charts they've got with the guy standing in the middle and it's high and it does that. That's perspective. But it's not doing the same thing this way as fast, because this way is a lot farther, because there's no hard limits on the side to narrow it down. Like the ground is narrowing, the ground is coming up, so it has to meet the ground before it just disappears. So I hope someone can explain that better or put it into other words. I'm just coming off the top of my head on that. So that's my idea and theories on why boats and sun disappear into the horizon the way they do. The next thing that I think I want to share with you on my ideas and theories is the concept of buildings on a globe versus flat. And I will use these two remotes here to demonstrate this. I'm left-handed, so it's easier for me to get on this side, or I'll get back here. Let's say these are two skyscrapers. Get out of it. So these two skyscrapers are on this ball Earth. Well, they're not going to be parallel with each other because if this is here, as this one goes around the curve, it's going to lean away. So the top's going to be farther away from the other building than the bottom. Can we agree on that? I know this is not the scale, but this still shows you the point. So the buildings here, I may only have like, say 8 inches between here and here, but I've got a foot between here and here. See that? That's a very noticeable, that's a noticeable difference between the top and the bottom. So I think if we could go to a large city like New York, where I know the island of Manhattan, I mean, I don't know exactly, but I've been there one time, and I know it's isn't Manhattan got to be at least 15, 20 miles long, if not more? And it's solid buildings. I mean, it's buildings the whole way. Surely you can get on the very end, the bottom, down in like Battery Park, and get in one of the tall skyscrapers and have line of sight up to the northern part of Manhattan, up to, Harlem or wherever that is. I can't remember exactly how they're laid out, but I think it's Harlem way up there. Or somewhere where you have a line of sight maybe 10, 12, 20 miles away to a building. And we should be able to measure, this variance, from the top of the buildings to the bottom. Let me see, this one should be more like that. This one's here. So, why are we measuring this? There's got to be a device, and I know somebody out there knows the best way. I'm not sure. Is it through lasers? I mean, there's got to be an electronic device that can measure distance from one point to another. I mean, that's how boats work, through sonar and radar or whatever they use, or through how planes find the distance to objects or whatever. We ought to be able to present that, at ground level versus up high, or maybe have to do it across a body of water, like do it from Manhattan over to New Jersey, looking across the water, so there's nothing in between, or any two cities. But you have to be able to measure from one building to the other at the base, and then go up as high as you can. You want to go as high as you can, because the farther you go up, the farther they're going to be apart. And get up as high as you can. It'll have to be the lowest common denominator of the two buildings. So if this building's 50 and this one's 100, you can only go up 50 in this one, because that's as high as you can go on that one, and measure across to that other building. And you should see an obvious, measurable difference between top and bottom if the Earth is a ball. And I think this should be a fairly easy experiment to do with just the right equipment and the right environment. Finding two tall buildings far enough apart where there's going to be a noticeable curve in between. Needs to be, I would imagine, assuming we're on a ball, you want to make it probably, and I know there's got to be a formula, and I haven't even sat down and tried to figure it out or looked it up, what the difference, but I'm sure there's angles here that tell me exactly what the distances should be between the top and the bottom, depending on the distance. That's another thing. If someone could make up a spreadsheet or a formula like we have for the curvature, the curvature formula, just input the factors and give us an answer. If a building is, and maybe do it in feet, or mileage. I would say you'd have to do it in feet because the difference up at the top to bottom is going to be measurable in feet. I don't think it's going to be a quarter mile apart. I think it's going to be within, just spitballing, like from the top of Manhattan to the south side of Manhattan, in that distance on a globe. I'm just going to guess that you may be looking at 15, 20 miles, maybe a couple hundred feet. Could be a couple hundred feet at that point, difference between here to here, which would be very measurable and very noticeable. And it's the same way, on this same principle. If we're on a ball and I'm standing here, of course I'm just a little guy and this is a high rise, the farther that gets, that high rise is leaning away. I'm not leaning, I'm perpendicular to the ball here. If you come around to the side, look at it. It was up here, it leans. Now, of course, this is way out of scale, and it's not going to be this drastic that quick, but it will be this drastic. But, we're only talking on globe Earth, maybe seeing this distance right here. But then again, you're only talking about a high rise that can't even be felt with if this was an actual globe, and you wouldn't even feel a high rise as a little blip on this. It's so small, you couldn't even feel it under your fingertips. So we're talking tiny, tiny measurements on something this size, but in scale, you should see, when we look and see buildings 20 miles, when we look at the Chicago skyline or Toronto skyline and see them mirages, well, why aren't they tilting away at 60 miles? That building should be, tilted away from us. That big old tower in Toronto with that needle coming off the top, that thing should be like this, man. It shouldn't be straight up and down. But every building we see off in the distance is straight up and down. Not only that, but when we're looking straight ahead and seeing the horizon, and we see that skyline stretches across that whole horizon, like the Toronto skyline, it's really wide. The buildings go forever. This is what we see. Oops, I'm dropping, sorry. I'm trying to look at the screen. Do this, I should look at my hands. This is what we see. What we should see on a globe Earth is this. The building should slowly curve, so the top should get farther apart. And we should be able to see that across the stretch, all the miles that we can see across that horizon. But yet the buildings just stay perfectly straight up and down with one another. They don't do this at all, which you would have to see. There's no way you couldn't see that if we're on a globe. So I think we need to kind of focus on, if we could focus some of our resources, or somebody has the capability that lives in a city with buildings like this, or where this environment is right to measure from one tall high rise to another very accurately. I mean, down to the foot, maybe to the inch. I don't know what the technology is. I know there's got to be something you can shine, a laser of some sort that'll, send a signal back and give you a reading. I know it exists. I don't have it. Maybe you do, and you're the person for this experiment, or who has it or how to get a hold of it. But we need to do that. That's science. That's a fact. if the buildings are on a level, flat plane like we say it is, then there's not going to be any difference from top to bottom. That's just the way it is. But if we're on a ball like this, the buildings are going to lean apart at the tops, and it's going to be wider here than it is here. It's just the way it works on a ball. You can't argue that, but you can experiment it and see if it exists. This is the theory. We live on a ball. So if we're on a ball, we know this to be true. This has to be true. This is a fact. So if we're on a ball, this exists. So let's just test it and see if this exists. It's very easy to test. So somebody needs to get on that. Seriously, that's what we need to focus on, that thing right there. Because I haven't seen those experiments online at all. I don't see it in any of the documentaries. I've heard it maybe alluded to once or twice in a very passive way, but nobody's taken the time to do these experiments that I know of. Maybe I'm wrong. If they're out there, let me know. Okay, my third idea is, this isn't my idea, but it's just an encouragement, because I think this may be the holy grail of proofs for the flat earth. And what I'm talking about is the old gyroscope. And I've really been digging into the mechanics behind the gyroscope here lately. And I don't have a gyroscope here with me, but I've used them in the past enough to know how they work. And I've watched enough videos with enough good science in it to what I believe I have a good basic understanding of a gyroscope now, at least enough to know. I'm not talking about getting into playing gyroscopes with, you know, pendulum things and pendulum limiters and things like that, self-levelers and stuff. I understand a little bit of how that works and all, but we're not focusing on that. We're just talking about a good old-fashioned tri-axis gyroscope that's free on all three axes. It's free to act on its own and not be influenced by any rotation of the base that it's mounted to. And with just a good old-fashioned gyroscope, Foucault said that he did this experiment way back in the day, and he used this gyroscope to prove that the Earth rotated. And I think we know now that that was just a bullshit experiment. Here he's got this old-fashioned gyroscope that, you know, compare it to our machinery these days, it obviously wasn't going to be built to the exacting standards. I mean, I'm sure they got it nice and good and a lot better than I could probably do, but I'm just saying the bearings aren't going to be the greatest. You can guarantee it. And here he can only spin the thing up so fast. I've seen that some people say he probably only got it up to a couple hundred RPM, you know, maybe 300 or 400 RPM. So what? Maybe he got up to 1,000 or 2,000, whatever. The point is, it would only be usable for a limited amount of time. And we're not talking about a large amount of time either. He could probably spin that gyroscope up and probably get 3 or 4 minutes, maybe 5 minutes at the top of usable time with it. So in that 5 minutes, he has to, he's got this long metal rod coming off of it that's welded to it, coming over here to a plate, and this metal rod lands on this plate, and this plate has markings on it. So if that gyroscope moves, you know, way over here, a little movement over on this end is going to be a bigger movement on this end, just because you've got the wire coming off. So, and then he had a little looking glass looking down on the end of this, because even the movements there were going to be so small, he had to have a magnifying, like a little microscope looking thing to visually see the movement, because he only had 5 minutes or 2 minutes to work with. And so in 2 or 3 minutes, the Earth's rotation at best is going to go, I think I think it's what, 10 degrees every hour or something. So it's like 3.7 degrees every 15 minutes. So 5 minutes is going to be just over 1 degree. So you're talking 1 degree of rotation of this ball, which is 360 degrees around. So in 5 minutes, it's going to go 1 degree. That would be measurable, maybe, in 5 minutes. But on his ancient equipment, he's just getting standard this variances in the bearings. When that thing's spinning, if the bearings aren't good and that wheel isn't weighted perfectly, any little, I mean, it's like your tire. Your tire's out of balance, you go to the tire shop and they hammer a little tiny weight on the side of it, just a little teeny weight on this big ass heavy tire, but they put this little tiny 1 gram or 2 gram weight on it, and your car can go from doing this to just running as smooth as silk. And that's the difference in the precision of these bearings and these gyroscopes. So any little bit of machination, when he made that gyroscope, is going to work itself out, and any little vibration is going to cause that little plate to move a little tiny little bit. Remember, it's got a wire coming way out of it over here, so the little bit you see here is magnified from what it actually was here. Here it could have been, it might have moved just, if over here 1 degree was a millimeter, over here 1 degree is going to be a couple inches. So if it still just moved a millimeter over here on this plate, heck, over here, that's just a variation, probably just the wobbling of the machine when it's working. The thing probably sat and done this right here. So our gyroscopes today are way better and way more accurate, and I can't tell you how many videos I've watched of people spinning up a gyroscope at 10, 12, 15,000 RPM, and then, the ones that use the air pressure even faster than that, and sit and put a time lapse on them and watch it, and they just don't move. They just period don't move. And guys, I believe we got the holy grail in the gyroscope. You can argue about a lot of things about this flat earth theory. There's a lot of debate that needs to be had. But I'm going to tell you, the gyroscope is our holy grail right now, or one of a few holy grails that we have, that you might as well print the textbook right now and put a gyroscope in there. I mean, we've all seen the video, unclassified, from the military, showing how gyroscopes work in airplanes. And this is the plate that holds the gyroscope to the airplane, and here's the wheel of the gyroscope spinning. Well, as this plane goes around the curvature of the Earth, this gyroscope is completely independent of any gravitational field. It's not affected. That's what happens when the plate's just standing still like normal, like this is. Gravity wants to just pull it down, or what they call as gravity, we call, electromagnetic force or density and buoyancy, whatever it is. We're working on it. We're looking into it. We don't have it all figured out either, but we're not just going to make up some bullshit and call a name to it just because it has to be some magical force that we don't know about. But the point is the natural pull of things is going to pull this metal plate to the ground or toward the ground. Well, once you spin this wheel up, this is like a heavy metal wheel. It can be huge. It can weigh thousands of pounds, or a pound, or even less than a pound. Just depends on the accuracy and all that you're going for. But when that bad boy spins up, it takes on its own qualities and its own physics. It it detaches itself from relating to gravity or the downward force that pulls on everything, because it builds up momentum and forces. It has several forces working in it, like atomic forces and linear motion. It has inertia. It has centripetal force, centrifugal force. So you've got all these forces working that gives it lift, and this thing becomes independent. Now it's relative only to itself. Wherever you put it, you can manipulate this in any direction you want. But wherever you manipulate it to, it's going to stay until acted on by an outside force. And that outside force has to physically mess with the chambers that the gyroscope is in physically, because it's on a tri-axis that's completely independent from the cage that's holding it. This can move in any direction. This is the cage holding it to whatever it's in, like a car or the device or your phone. But that wheel of the gyroscope is completely independent in all three axes. So a plane flying through the air can be doing barrel rolls and tumbles and doing all this, but that gyroscope remains straight up and down and accurate. That's why they can look at their instrumentation at all times and know exactly where the horizon is. They're not looking out the window or they'd be barfing everywhere, because the shit would be just doing this. They're doing barrel rolls. All they got to do is look at that instrument panel and see that line on that horizon, that artificial horizon, and line it back up, pull on their yoke or turn it, whatever they got to do to get this to where their horizon is back level. And that's all what this gyroscope does. So we're going to take just a standard gyroscope and just spin it up and set it on the table. Like I got a table right here. Let's say we spin it up and set it on here. Now that video that we can see 1,000 times on Flat Earth, that old black and white military video, they literally show this gyroscope going around the Earth, and the gyroscope maintains its upright position even as the plane flies around the Earth. It actually says this in a video explaining gyroscopes, that they have to be manually calibrated every 15 minutes to the magnetic compass, because they lose their calibration because of the curvature of the Earth. So we know for a fact that a gyroscope is free and independent of gravity. So we ought to be able to set a gyroscope on the ground right here, right? This is the ground where I live. I spin up a gyroscope and set it down. And then I just wait for this Earth to spin. Of course, it's always going to be on the top as far as its center of gravity where I live. But as this Earth spins, this gyroscope, which was once this way, should remain flat, see, because it stays in the same position in relation to itself. It should be in 6 hours. If I'm on the equator, it's going to be different at other places, but you can figure out. It's going to have moved, and I should be able in 6 hours to measure the different angle, because this is ground. I'm at 90 degrees. See, I'm perpendicular to the ground. Now I come up here and I'm parallel to the ground. That's a big difference, and that's measurable. And we should be able to easily see that in a gyroscope. Yeah, we just sit on our kitchen counter and wait 6 hours, put an electric motor on it where it's constantly spinning, or get one that hooks to an air compressor and just keep it running and let it constantly run, or whatever, you know. But in 6 hours, if we're on a globe, according to their own propaganda that they put out, that gyroscope is going to show the turning of the Earth. It literally says so in that video. It says it will be in 6 hours, it will be at a 90 degree. And you see this white spot on their map, that represented Antarctica, and they were doing it here, so it was around the equator. It will only work at the equator because according to their theory, the Earth spins on an axis. So the only place you're going to have a full spin is on the equator. If you're up here in America, you're only doing rotations like this instead of like this. You know what I'm saying? So in 6 hours, a 90 degree change will only be evident if you're at the equator. If you're up here, it's going to be a little different. You can get the math and work that out. There's another video I was watching just earlier that was actually showed you how to figure that math out. So, but I do believe that a gyroscope is our holy grail. I think we all need to invest in gyroscopes. This can be our thing we take around with us everywhere we go. We can set up a table out in downtown somewhere, and on the weekends when everybody's walking around town, set you up a little flat earth booth and have you a gyroscope out there spun up and put a clock on it and let people stand there and watch it, give them some, let's watch and see it. Here, watch a gyroscope turn with the curvature of the Earth, Foucault's experiment, and get them out there and you turn and spin it up and you get them to watch it for 6 minutes or 10 minutes and it doesn't move, not nary a bit. Then you say, well, why is that? Then you talk to them about the flat Earth, because they can't deny it's science. You understand what I'm saying? You can take and pick up that gyroscope and just flip it in any direction you want and show them it ain't moving. You can take and do it like this. G-forces don't matter on it because it's independent. It has its own independent force. Once this plate spins up fast enough and the inertia going out, the atomic force, and the centripetal force, the pressure pulling in, it all comes to a nexus depending on how fast and how heavy this thing is and everything, but it'll have its speed. And once it gets rotating so fast, it takes on its own qualities and it just lifts. You can get a gyroscope made with a 1,000-pound metal plate, a brass disc, 1,000 pounds. Me and you wouldn't be able to budge it. But you could spin that bad boy up fast enough and we could pick that whole thing up with our finger. We could pick the whole housing up because it's independent of gravity. And move it around because it's just how it is. They're amazing devices, and I think they're going to be our holy grail if we focus enough attention. And there's been a lot of videos done on it, which I think people understand. The gyroscope is the holy grail of proving the flat Earth because it does two things in one shot, or it kills two birds with one instrument. It proves the Earth is flat, and it proves it doesn't move. It proves it's flat by, if you take a gyroscope in a plane and fly, the gyroscope doesn't do this. The gyroscope always stays perfectly perpendicular to the ground. Well, it can only do that if it's on a flat level because the ground hasn't changed in relation to the position of the gyroscope. Remember, the gyroscope never moves from its position in space. Wherever you initially put it, whether it's like this or like that or like that, that's how it's going to stay, boys, until somebody reaches up with some object and it physically manipulates it to the position they want. But in that housing doesn't affect it. That housing can do this around it and never, because there's bearings and it's 3 axes of bearings. So you see, I don't know if you've ever been in Orlando, where I'm from, downtown, in Church Street Station. They had a little thing you could you could put your arms in and walk in and your feet, and you're like in this gyroscope. And then they unlatched the 3 different big steel cages you were in and started spinning it. I think it had an electric motor, or maybe they did it by hand. And here you are flipping around, just doing all this, but yet it feels like you're free falling because it's completely smooth motion. There's no jerking because it's when you have those bearings on all 3 axes, it's smooth motion. It's completely independent on any outside force other than its own spin. So once that plate slows down enough and loses its momentum and its inertia, then it begins to interact just like when you spin a top. When you were a kid, you had a top and you pushed down on that thing, and then boom, that top would just spin just so nice. And then all of a sudden it would start to recess, and you get recession, and then all of a sudden it would hit the ground and roll and stop. Well, if you spin that top fast enough, that boy will just stand up as smooth, as straight as possibly could be. I mean, thing will just sit there like it's not even moving. You'll touch it, and it'll be like, but it looks like it's not even moving. It's because it's balanced. Well, that's how gyroscopes work. So I think we need to focus more on gyroscopes. It's our holy grail if we'll pay attention to it. I mean, it can't be disproven. It's science. I mean, I watched a video where a guy was driving down the road in a semi-truck, and he's like, well, guys, I know you like to use a gyroscope to prove the earth is flat, but I'm going to tell you something. Gyroscopes have a pendulum in it, and therefore, you're wrong. End of video. And it was like a 2-minute video, and this was literally his evidence. So a guy driving down the road in a semi-truck just saying something is automatically true science or something. Why didn't he get a gyroscope and open it up and show us these pendulums he's talking about? Well, the point is these home gyroscopes don't have these pendulums he's talking about. Yes, there's pendulum limiters and stuff and correctors on artificial horizon air induced gyroscopes that they use in planes, but there's like 4 little slots in the side of the gyroscope that have little doors that slide. So if the gyroscope gets out of its coordination, if it eventually shifts from the vibration of it, in the moving of the plane eventually has a cumulative effect on the position of the gyroscope because of the bearings and stuff. This gyroscope, the spinning part, has these 4 plates, which are called like pendulum whatever, and they open and close and let the air that's shooting through, that's keeping this thing spinning, is caused through compressed air spinning through it. So if it tilts, the door will kind of shut, forcing more air to come out another side, and it'll straighten it right back up just from the air pressure, which is a great invention, a great way, and I'm sure it works. But that's not what we're talking about here. We don't care about the gyroscopes with the pendulum. We're just talking about a standard gyroscope, 3-axis gyroscope that's completely independent of its base in any direction. Let's get one of those on a plane and see what happens. Can someone get one of those? Can someone get a gyroscope with maybe a battery operated motor or something and get it onto a plane? That way, 10 minutes of flying time is like 3 hours of waiting on the ground, as far as going around the earth. So in 10 minutes of spinning up a gyroscope, even if you had the string pull it, that's going to be like looking at one for hours on the ground, because you're flying a long distance quick instead of just waiting for that to happen. So let's get one of these on a plane, maybe call on the plane or whatever. I know you're doing your phone, and those are great, but I think with the accelerometers, I think we're kind of barking up the wrong tree with that. Not because it doesn't work, but because it's hard to prove. You understand what I'm saying? it's hard to prove that that's what this is doing because there's so many rebuttals, but gravity, but it's always pulling, it's always adjusting itself, and we don't even know, to be honest with you. We still debate this. I mean, not everyone is sold that the accelerometers in here should do what we want them to. Now, we know the Earth is flat, so no matter what, when we go from Seattle to Dublin, like Paul did, it's going to stay flat because we know the Earth is flat. But we're trying to prove it using something that would work if it would be a ball. It has to be something that would prove it's a ball. Like, so we're falsifying that the Earth is flat. We say it's flat, so use an accelerometer to prove it's a ball. I don't know if the accelerometer will do that. That's what Paul in the Plains videos are proving when he takes his phone and the spirit level and he sets it and turns it off and turns it back on, and it's still at the exact same level that he left it on the other side of the Earth, And yeah, that seems to prove that the Earth is flat because that's what you would expect on a flat Earth. Well, there's also people saying, well, yeah, that's also what you would expect on a ball Earth as well, because you've got gravity, that the phone is basing that position based off of its downward gravity pull. So when you come over here, gravity's now this way, where up here it's down. So maybe the phone knows that gravity's pulling that way now, so it adjusts for gravity. So you would expect it to be level here. And I understand that they're saying that the accelerometers are independent of gravity, and they probably are. Maybe they are. But it's hard to prove. There's a lot of room for debate. And why do we want to spend time on things that are easy to refute and hard to prove when we can take a simple gyroscope and actually prove it, and there can be no debate? You understand what I'm saying? This is a lot better than the phone, is what I'm saying. I think we should spend less time using the phone to prove it and use more time with the gyroscope. Okay. Next thing, of my ideas and theories. I keep hearing this rebuttal about, well, if the Earth was flat, then planes, circumnavigating the Earth, depending on the direction, would constantly have to be correcting east, left or right, because on the flat Earth, north is dead in the center like a record player, and just like the grooves on a record, that's east or west. If this is the face of the flat Earth, okay, forgive me for using the ball, but just pretend like this is two-dimensional and it's not a sphere. This very center point is the North Pole. That's south, that's south, that's south, and that's south, right? Because this is the center point. So from anywhere on the ball, north is wherever that center is north. So east and west are this way. So if you're on a flat Earth and you're going east and west, circumnavigating in an airplane, it looks like you're going to constantly have to be turning, turning right or left, depending on the way you go, to compensate, because you're going around the disc. You're going around the circle. Not around the curve, but around the flat circle like a record, like you're the needle going around the record. That's circumnavigating a flat plane, which is, there's no conflict there with circumnavigating the Earth, because you can still circumnavigate your dinner plate with your finger. Just do this on it and make it sing. Remember how you used to do that? Circumnavigating. Well, the thing is they try to tell you, well, the planes have always got to be, adjusting for that turn. Well, I've got bad news for you globies, globulars, globetards, retards, whatever y'all call yourselves nowadays. You still got the same problem on the spherical Earth. The only way that a plane won't do that is if it's going directly around the equator like this. Like a full circumnavigation, all the way around the full circumnavigation of the Earth. But if it's up here and wanting to go due east, or yeah, this would be due east, do you not see the plane turning? The plane is no longer flat like this, it's now tilted like this, see? Here it's flat. Up here it's tilted. So now it's not just going like this, it's also got a bank, right? So you have the same issue that we do. There's no difference. The only way you don't have that issue if it's going directly around the equator. Because south of that, now you're going to be turning the opposite way. But you're going to have to constantly correct. Well, there's a simple answer for both of these. If this is my starting point and this is my destination, or let's say starting point here, I'm going on the same line, you know, and here's my ending point, we're on the same line. I don't have to fly the longest way around due east or due west. If I'm on a globe, I can come straight across and take the equatorial path, meaning the straight way. This is not straight, that's the long way, even though it's following that east-west, what is it? Longitudinal line? Yeah, longitudinal line. But I wouldn't fly that way. If I wanted to fly straight there, I'd just pull a string and go and fly straight as if I'm going around the equator. I would fly straight. I wouldn't go around the curve unless I had to because that was required in my flight path. I've seen videos where they show from like China and Japan and all that over here on the Pacific, going across Pacific Ocean to the U.S., the planes coming this way take a northern flight path, and the planes from the U.S. this way take a southern flight path, you know, kind of like, you know, driving on the right side of the road, where you're flying so where planes aren't flying in the same airspace toward each other. So you got planes flying this way and planes flying this way. So this curvature is already built into that flight path. So they expect that. You can watch, who was it? I'm not sure if it was Paul on the Plane or somebody has done a lot of time-lapse, you know, filming of their planes all the way around the Earth. They've flown all over and they've recorded it. And what you notice is planes never do this. They never take a slow bank. They fly in straight lines. So they'll fly perfectly straight, and then all of a sudden you'll see, of course it's time lapse, so it happens quick, but it could happen over a period of 30 seconds or a minute. I don't know. I've only flown one time in my life, so I can't quite remember. But on the video, you'll see the plane will fly just straight, then it will just correct itself, and then now it's going this way. It never does this. They always fly straight, and then they'll bank it and then go straight from there instead of just taking this curve. So it's a foolish argument to begin with because that's not how planes fly. Not from what I've seen, not from my own experience, and not from just what makes logical common sense. So this whole thing about planes having to turn around the globe, around the flat Earth, so that's a problem, is not a problem. You've got the same problem here that we have on the flat Earth, which is not a problem because on the flat Earth, if we're just going to take a straight line, guys, we're not going to do this when we can just go straight across. I mean, are we retarded or what? So, well, I look tired as all, don't I? Well, it's only 1 o'clock in the morning, but who cares? So I hope I explained that whole planes flying east-west bullshit and debunked that. Okay. Next, mountains. And this goes back, remember the 2 remote controls in the buildings I think we should look into? There's another thing. I'm wondering what I can use here. Okay, I'll use this and this. These are about relative in sizes. Using Pythagorean's theorem, you know the chart we're all familiar with. It's got the little circle and then the line coming out, and the ones coming down showing the increments, and over here is the chart that breaks down the miles and how far the drop should be based off the formula of, you know, distance squared times 8 inches. So let's just say, and I'm just using bullshit numbers, but let's just say this building here just so happens to be exactly even with our line of sight, you know, if we were on a ball looking straight out, our eye level, and this building is 1,000 feet tall. I'm trying to stay out of the way of it. What if I come down? I'm just trying to get better perspective here for you on the camera. You know, it's not the easiest using these old-fashioned demonstrators. But anyways, you get my point. So this building's 1,000 feet tall. So what we do, see, we follow that line out to that building top, and we say, okay, that's 1,000 feet. So whatever that chart tells us 1,000 feet of hidden should be, let's say, I don't know, I don't have the chart, I should look it up. So do not use these numbers. This is pure pulling it out of my ass. But let's say 1,000 feet is 40 miles. I think that's about right. Across Lake Michigan, it was about 40 miles, and it should have been about 1,000 feet if I remember right. But let's just say, so that's a 1,000-foot building, so we say that's 40 miles, right? But that's wrong, because look at what I'm doing with this lighter in relationship to the Earth. It's not perpendicular to the Earth. It should be like this. It's going to follow the lean. So I've got to come back to here. So that building disappeared way sooner than we think it does, only because it's leaning. When something leans, it loses its height to our perspective. If that building is going around the curve and leaning, the top is losing its height as well as it going around, right? Because it's not going around like this, it's going around like this. So when it comes to buildings and even mountains or anything, they're going to stay perpendicular to the ground they're attached to. So the base is actually going to be closer. Now, I think we can probably get a formula worked out to figure out, you know, to compensate for that depending on the height of the object we're looking at. So if we're looking at a 100-story building, we should be able to type in, okay, a 100-story building should disappear when? And it should have to compensate for the fact that the building leans over. When we're doing our Pythagoras theorem, we're not compensating for the building leaning at all, are we? No. So we have to compensate, which changes the base tremendously. From there, from like there to here, you know, that's a difference. And that's going to be noticeable. So all I'm saying is when we look way off into the distance and we see a building way out there, it should be leaning away from us. The farther it goes, the more it should lean, and that should become noticeable. And that's going to affect, it's going to affect this measurement we've been using as far as where things disappear. Now, if it's something right on the surface, like a boat that's not very tall, yeah, it's gonna not, that little bit's not gonna make a difference. But when you're talking about a high rise that's 100 stories tall or more, or 70 stories tall, that can be seen from 50 miles away, you've got some leaning happening, and that top of that's actually appearing shorter than it really is because not only did it go around, it's leaned on you. So you're going to lose it quicker than you think. You don't have to go 40 miles to disappear. It may only have to go 35 because of the curvature. We're not taking that into account in that equation there. Yes, the distance from the top of that completely horizontal line to the ball is Pythagoras theorem, 8" times distance squared. That is the accurate measurement between there and there. You know, between here and here. So if from here where you're standing out to here is 100 miles, you just do 100 miles times 100 miles times 8 inches, and that's your distance. But buildings don't stand up like that. They stand up like this. So that theory is not accurate for tall buildings and mountains. You understand what I'm saying? This should thrill us because it's for our benefit. It actually helps us out. It gives us more room to work with. Like when you're standing on a mountain, seeing another mountain 70 miles away, and we see that mountain standing straight up, we ought to question, wait a minute, if we're on a globe Earth, that mountain should appear to be leaning over. Hell, I mean, at some point it almost looked like you're looking flat across it, but you're really looking up it, but it's just over here far enough where now this is the rise of it, which was up here at one time, now is over here, so it looks flat to you from up here. I know we're not going to see it that far, but if we could see that far, and we didn't have limited range of eyesight, which we do, that's just, we can't see this whole plane because of our limited range of eyesight. That's the whole reason. I mean, we can only see so far. Heck, there's atmosphere here, guys, and all kinds of other stuff. It's not complicated. I mean, whenever anybody says, like Bill Nye, why can't we see over to Spain from New York, you know, they're just not being honest with themselves, or they're just trying to argue, because everybody knows you've got to look. I live here in the mountains and I drive, and anybody who lives in the mountains knows the mountain right here in front of you is crystal clear, and then the one right here gets a little blurrier, and the one back here is real blurry, and the one back here you can barely see. And you're only talking like 20 miles maybe, and the mountains disappear. You literally see the distinctions between the distances and how they fog out simply because of the air, but yet it looks like a crystal clear day. Blue skies, crystal clear. We say, hey, this is a clear day. You still go out and the mountains disappear. They don't all stay visible as far as the eye can see for thousands of miles. You're lucky if you can see on a super clear day, what, 100 miles? I don't know, but I think from up on top of some mountains, I can see about 100 miles on a clear day. And I'm going to tell you, it's limited, because eventually there's atmosphere. You're looking through a sea of atmosphere, whether you're on a globe or a flat earth. We have an atmosphere, and that atmosphere is like an ocean of water and mist. We're so close to it right here, you can't see it. But you ever heard of humidity? That's the amount of moisture in the air. And when humidity's high, there's a lot of moisture in the air. You go out to the beach, you're already looking across water where the moisture's evaporating from. So you're looking through evaporating moisture, sea spray, through waves crashing, through mist in the air, through rainstorms and hailstorms, and who knows what else is going on between you and there. How in the world do you expect to see more than 100 miles or so? It's ridiculous. So the thing is that we need to work on that things angling away out of our line of sight on like tall buildings and stuff, because we ought to lose them actually quicker than we think. You understand what I'm saying? So these are things we need to work with. Okay, going on to the next thing. We need to do some coordinated sun position, you know, and angle studies. This should be super easy. Like I'm here in the mountains of western North Carolina. Flat Earth asshole, I think you're in California or wherever you're at. And somebody in Michigan, and somebody in Texas, somebody in Alaska, somebody in the UK. You know, we need to like set up a time on any particular day and be like, okay, at this moment, right now, all of us at the exact same time, go out and measure the angle of the sun based off of a stick we put on the ground or whatever. You know, and do our own sun angle experiments. But with where you can have 50 people give numbers all at the exact same precise moment from 50 different places around this country. We should learn a lot of information with that, and it would be very easy to do. Hell, with the social media, we could have this experiment done tomorrow if we wanted to. It don't cost anything. We already exist. All we have to do is go out at a specified time. So if it's 1 p.m. Eastern time, then it's going to be, you know, 10 o'clock a.m. Western time, because West Coast time, because we want to do it the exact same moment, not wait 3 hours till the sun comes around to yours. No, we want to do it at the exact moment in time everywhere as far as we can around this globe. And let's just take a snapshot from our own observations of people on the ground, not from a computer or NASA or a website telling us where the sun and moon should be, but take our own observations all at one time, a bunch of us, and just compile the data and see what we find out from it. I think it might tell us something. And another thing we need to do, I'm almost done here. We need to do a bigger and better and amazing bed for level experiment again. We need to modernize it. These clowns that tried to do it, I'm sorry guys, I appreciate your effort, but believe me, you wasted your time and pissed a lot of people off that watched that video because it was pathetic. We need to redo the bed for level experiment right. If that means getting out there with weed whackers and whacking down all that marsh that was sticking up, you know, we need to do what it takes to do it right. We need to get out in the middle of the water with a telescope. I mean, come on, let's get wet. Get a wetsuit, a diving suit if you're scared of a little cold water or muddy water. Get someone who's not scared of it. I grew up in Florida and playing in lakes. I mean, it's in swamps. You know, I've been on mud walks where your shoes got sucked into the mud and you'd have to fish them out. You know what I'm saying? So there's people that'll do it, but we need to do it right with good equipment, good lasers, doing it the proper way, close to the surface of the water, and we need to redo that and televise it. We need to build it up, hype it with the media, and have it televised live. A modern bed for level experiment. We're bringing it back. These crazy, ignorant fools think the earth is flat and are going to prove it live on TV. Just like Geraldo Rivera live on TV was going to show us the contents of Al Capone's vault. Or just like Richard Madcow was going to show us Trump's elusive tax returns. And you know how they hyped all this shit up? Well, we can do this. These lunatics are going to try to prove the earth is flat on live TV, and then we prove it's flat on live TV. You see the twist there? You see what I did there? We actually do it, and minds are blown on live TV, but they think they're going to trap us. So somehow we can probably get this done. I don't know. I don't think I'm the one that headed up, but I'm just spitballing right now. Okay, next thing. Another Holy Grail that I really believe is the second best Holy Grail, or maybe the first, with the gyroscope, which everybody has access to. No, but not everybody has a gyroscope, but everybody has access to this, is the night sky. I believe the night sky could just be one of our best Holy Grails. And I'm talking about star rotation in the North Star, Polaris. And we all know what happens. We all know the North Polaris is due above the North Pole. And from wherever you're at on this flat plane we live on, you look up to the north and set a time-lapse camera, and that sucker does not move. It stays right in one place, and all the other stars just circle around it. Well, if I printed a bunch of stars on the top of the ceiling here in the living room, and I just started turning my head like this, or I took the phone and recorded it and just started rotating the phone, I could get one if I'm careful enough. I'm super precise, like maybe I have this on a pedestal and it's on a swivel that's perfect. I could spin it, and then one star, it would find itself. It would be the one that doesn't move. It would be the center star. Whatever one that is would be called Polaris. And all the other ones would just rotate in concentric circles. But that would only happen if I'm right here looking due north, right? Because if I'm over here, now the North Star is up here to me on an angle instead of here, it's here, right? But yet this ball is rotating. So I'm doing this, looking up at a star on a tilted ball. So this is like, and I seen a demonstration where a guy took a laser, pulled a string, he had it on a globe, and pulled a string up to the ceiling. And what he did is he pulled a string up to the ceiling on the 23.4 degree angle, and then where he was right here, so this was a laser. He got it to where it was shooting dead on the ceiling where that string was connected, and he taped it. And he said, what do you think's going to happen when I rotate the globe? Well, you would think, well, you're just going to rotate it. It's going to go in a circle, but the laser's going to stay on the string. Well, the Earth is at a 23.4 degrees axis. If it was straight up and down, that would have worked. But the axis fucked it up. And when he went to spin it, the light came off of the center and came around and kind of went like this. So if you would have had a time-lapse photography of that, you would have had a bunch of spirals like in the sky, but there wouldn't have been one in the center and a bunch of just concentric rings of stars around it. You would have had more of a bunch of circles like kind of around based off of that. And then not only that, we're supposed to be doing this around the sun as well, and the sun's doing this around the galaxy, and the galaxy's doing this around the great void. We're moving in all these different directions, and for as long as we've been on Earth and we've had recorded history and star charts, we still see the Big Dipper. We still see the same exact constellations, bro. They haven't changed. And let me tell you, do you understand if these stars are trillions of miles apart from each other? I mean, let me get this experiment how I have it, how I want it. Okay, see these two things? They kind of, by illusion, look like they're the same level. But if you come around, you'll find out I've actually got them that far apart. See what I'm saying? That's called parallax. Well, we should see that depending on what angle of the Earth you're looking at from. If I'm at one point, I'm going to see these two stars like this. But on the other side of the Earth, I'm going to be viewing it from a different angle. Right? Because if I'm here looking up, or if I'm here looking up, it's this way. So I'm looking from a completely different angle at the same thing. So I'm seeing something from a different perspective. It depends on where I'm at, where that perspective is going to be. Well, hell, to make a constellation, you've got about 5 or 6 of these, in different depths in the sky, supposedly. That's what they tell us. Well, how come people over here, people over here, people over here, people everywhere see the Big Dipper and Leo and Scorpion and Orion's Nebula and the Belt and all the constellations perfectly. No parallax. There's never one measurement of difference between these stars, and hasn't been for thousands of years. But yet we're spinning on this ball, just flying through space, right? And the same stars, saying the exact same place in the sky, bro. If you can make that happen, that is supernatural, for real. That makes the Pac-Man theory look like child's play. Because I'm gonna tell you something. Those stars aren't going to be doing what we see if we're on a globe Earth spinning through space. That's just common sense. It doesn't take a rocket scientist to figure this shit out. I mean, this is just, come on, guys. Just do some simple experiments like that guy did with the globe, or just use your brain for a minute. Look at anything. Get 4 or 5 people and align them up like the Big Dipper in your living room. And just get one person to stand on one side of the room and then one on the other side, and look at these 4 people, and everybody is going to see a different shape of relation to people to each other, because it depends on the angle they're looking from. That's parallax. But we don't have parallax in the stars. And the reason is because all the stars are fixed and they're in one spot. They don't move. There's a few wandering stars that we call planets. Those are different. And even those have their own particular journey that they take. Just read the Book of Enoch or look in the night sky. But these stars are just lights for us. It's like a projection of a pre-printed, it's like a light bright. Remember the light bright? We would poke a bunch of holes in the black sheet and then pull them out and shine it on the wall, and you would see, you could make your own starry patterns with the light bright. Or they have the little rotating constellation lights you can put in your bedroom, and it'll shine the night sky on your ceiling, and it'll turn it like in real time. That's exactly what we're literally seeing. We're seeing a pre-printed projection of some sort, or physical lights attached, and they're rotating. I'm thinking it's projection only because they're all together perfectly, like it's on a piece of transparency that doesn't move, and it's just spinning, in a circle for us. It's our little timepiece. It's the numbers on our watch that are fixed in place that lets us know when that second and hour hand hits the 1. The 1 tells us it's 1 o'clock, and the 2 tells us it's 2. Well, these stars are our indicators of where we're at, and where's north and where's south, and all of these things. And so I believe parallax and star rotation, if we can invest some more time into it and really dig into this and get the physics of it, and some good experimentation, some good quality experimentation on a large scale of some sort, we can put our minds together and come up with it. I think parallax and star rotation is really going to serve us well in this argument. My final thought on these theories is Occam's razor, and we all know Occam's razor, and most of us do, and it just simply means the simplest is always the best. If you got a dog and you go into your living room and you see something shredded on the floor, Occam's razor teaches you that the dog chewed it up. You've got a dog and you've got a shredded pile, and the dog's got, lint hanging out of his mouth. Occam's razor says the dog did it. Well, you get a lot of smart people that try to say, well, what if, though, and come up with all these bizarre ideas. Well, Occam's razor is against that. Occam's razor says the simplest answer is usually the best answer. It's not always, but as a rule of thumb, it's the simplest is the best. So we should remember that, and when we present information or proofs to people, let's use the simplest ones, the ones that have the biggest impact and are easiest to show and the hardest to disprove, are the ones that are impossible. Why do we want to venture off into unprovable things it feels good to blow someone's mind with what ifs, yeah, but first you got to get them through them gates of believing that they're on a flat plane that doesn't move and that NASA faked everything they ever put out. And until you can do that, who cares about what's on the other side of the Antarctic barrier or what the firmament is made out of? Those are peripheral issues we can deal with later. You've got to get people to this very fundamental place. And I think we need to just not worry about any of that. We can look at it and discuss it and experiment, and we got to keep pressing in. We got a contingency of us whose passion it is to explore the outer rings of those things, and we need to fund that. We need to encourage that and coordinate with it and work together. But we also need a foundational core group of us who are just focused on explaining this scientifically and proving it where it cannot be disproved once and for all. Because we have history on our side, guys. You do know that. We have thousands of years of human history on our side. This whole thing right here is new. It's the new kid on the block, and it's retarded, and it's easily debunked. But we got to deal with this. We have to use psychology, man, because we're talking with human people who have a lot of pride and a lot of emotion invested in this thing. Think about it. How much emotion you had invested in this, and space travel, and going to the moon, and how much you've rooted for NASA. I grew up in Orlando, just 50 miles away from Cape Canaveral. I watched almost every shuttle that was ever launched go up. I watched the Space Shuttle Challenger explode right before my eyes. Okay? So I grew up on the Space Coast. That was big to me. So, you know, we've all got to work through this. And in order to do it, we got to beat the brainwashing. And to do that, we're going to have to get people at a raw. We can't beat around the bush. We got to bring raw science to them, because that's what's going to win it. At the end of the day, it's going to be raw, hard, cold, provable, or falsifiable science that's going to win this. And until we can perfect the art of getting our message out there, we're just going to be a loose hodgepodge of people that are in drama against each other all the time. And it's really self-defeating, you know. We are so much bigger, guys, than our own petty differences. I'm just trying to drive this across. We're talking about the earth being flat. Everything we've been told, every human for the last 500 years has been told, we live on this and we're flying madly through space. And we're saying we live on a flat plane inside of a snow globe. And God has his feet right on top of us, and he's looking down, because Earth is his footstool. This is what we're saying. Does that not blow your mind? Does that not make your heart race a little bit? Does that not fill you with wonder and awe of, like, God, Lord, Savior, Creator, Deity, Energy, Spirit, whoever, the Great Chief? We cry out to you in humility, in awe and reverence, because you're awesome. And we want to honor you and worship you in truth and in spirit. And we do that by loving one another, bearing one another's burdens, putting up with our differences, and putting our differences aside for a little while. There's enough of that going on in the world without us having to do it. We've got too big of a fish to fry here to split and divide over things like the church does. Let there be no divisions among you, it says, but we divide ourselves into thousands of denominations in the church. But he said, let there be no divisions, because you are all one. We're one, people. This flat earth movement, we're one. We have one goal. We have one vision here, to present this flat earth to a world who's deceived. so we can wake people up, so we can get things changed, so we can explore again, so we can take the shackles off of Antarctica or whatever's going on over there, or find out, so we can explore again. So I'm just encouraging you people, man, get excited about this. Love one another. Let's work together, guys. We've got to have each other's back. That's the only way. If we keep up this bickering and drama and the finger pointing, and we can point the finger at someone like I did in this video. I've called out several people's names specifically, but I did it with honor. I did it with respect. And I did it because my intention isn't to belittle somebody or bring them down or show them how stupid they are. But my point is that we can get on the same page and we can walk forward in truth. And that's all I want. If I'm wrong in my presentations of what I thought was bogus science, just show me. Remember the whole thing about changing directions? I can change directions if I'm wrong. I thought about this long enough before I said anything that I don't think I'm wrong about those few things I mentioned. But I could be. I don't think I am, but I'm open. Okay, let me close this so we can shut this down for the evening. I want to finish by, just throwing it out there. You can respond in the comments. If you hung out this long, you are a champ, and I appreciate that. I mean, I know this is long, but I would watch this. Believe me, if you put this video up, I'd be watching it because this would interest the hell out of me. I want to talk about live streams, doing some live streams. I'm not really familiar with that. As much as I'm up on electronics, I've not worked on, webcasting and stuff. So I would like to do live streams. If you're in the Western North Carolina area and maybe you know a little bit about live streaming and you want to help out producing these videos and work on this, let me know. We can get together. This is what it's about. It's finding out those people that are near you and coordinating and teaming up and pulling your resources together. Let's get some stuff done, man, in this area. And put your ideas in these comments down here. If you have any questions, any rebuttals, if you want to know something, if something troubles you, I'll look into it. I'll dig until I find the answer. If not, I'll go somewhere else and find it, or I'll tell you I don't have the answer, but I'll do my best because that's the kind of guy I am. I'm going to dig until I find it. So anyways, I sure do appreciate you guys. It's been the Flat Earth Genius. Let's keep our heads together, fellas. Let's use our minds. Let's be patient with one another. Let's love one another. No matter what your religious view is, let's accept one another. And recognize we're free, man. We got a big responsibility here, man. Let's kind of be aware of the enormity of what we're talking about here. We're not just talking about some cool thing we can tell the guy because we know something they don't. It feels good to know something somebody doesn't, especially something this big. But believe me, that's a flash in the pan. Those feelings come and go, and after a while, it'll get old. Because, you've felt it enough, it doesn't matter anymore. Those emotional things of having this information will come and go. But the truth is going to remain, and you have to keep that focus that we got a mission here. We need to work together to get this mission accomplished if we're going to figure this thing out, is all I'm saying. Okay, well, guys, I'm the Flat Earth Genius. I appreciate you. God bless you. Get in touch. I will try to respond to any comments I get on this. Pass this video around every way you see fit, Facebook, whatever. And let's get this thing going, guys. Stay in touch, man. I'm serious. 100. Peace.